You can get ketones and aldehydes. You can get aldehydes from nitriles by a single reduction with diol and then water or acid. So if you need to make an aldehyde, maybe depending on what you have starting materials, making a nitrile and taking cyanide and adding it in an SN2 fashion to an alkyl iodide, that's Chem 232 material. So if you can make a nitrile, you can make an aldehyde. And that's something people use all the time.
Professor?
Yes.
For when you hit the nitrogen and it got both of the hydrogens on it, I can see how the first one came from when water attacked the aluminum and the hydrogen shifted to the nitrogen. But how did it get both of those hydrogens on it?
Well, so the first one, this nitrogen, lithium, aluminum thing, there's a minus charge in this nitrogen. So the first time it's just going to act as a base and take a proton from water. Was that what you're asking about?
Yeah, and the second time is when the water attacks the aluminum and the hydrogen shifts to
Yes.
the nitrogen.
Yes, very similar to the diol case.
Okay.
So nitriles will go once with diol. The other cool thing about nitriles is if you throw a Grignard and you're really careful, it will just go once. So whereas esters, if you take an ester and throw in a Grignard, it will go twice to give you the tertiary alcohol. But the nitrile now, if you throw in one and throw in the Grignard, you'll get mono addition. Someone throw in an organometallic reagent like a Grignard or lithium they like. Anyone will do. Beuly? I hear Beuly and phenylmagnesium bromide. I'm going to go Beuly because it's easier to draw. Bu for butyl, minus charge, lithium. So again, you do this cold, minus 78 degrees. And so the Beuly will add once into the nitrile. And that will give us this. So here is why nitriles stop once, if you're careful. This intermediate has a minus charge in the nitrogen, right? So what's going to be more reactive than neutral nitrile starting material or the singly added intermediate? Right? This is not going to be as reactive because this is neutral, this is a minus charge. And so the reason this happens is because the nitrile, so in an ester, right, the ester can just kick off the OR group, giving us an aldehyde, which is further added by a Grignard. In this case, there's no leaving group. And so when the nucleophile adds once, it gives you this intermediate that's not going to be reactive because it's got this minus charge on this nitrogen. And so what that means is it's not going to be as reactive. Typically for a carbonyl, you have a positive, you have you have a partial positive charge here and a partial minus charge here. But now, since in this case, we still have a slight partial positive charge here, but now since this nitrogen is a negative charge, it's going to be giving some electron density to that partial positive charge, making it less of a partial positive charge, so because it'll be less reactive. And that's a kinetic argument. The thermodynamic argument is, if Beuly adds into here, then you'll have a bis, you'll have 2 minus charges in the nitrogen. Do you think it's the same atom likes 2 minus charges? No, you don't want to have 2 minus charges in the same atom. You don't want to have 2 minus charges in the same molecule, to be honest. So pretty much because this has a minus charge here, it's not going to be reactive at all. So the Beuly is going to add once, and this is just going to stay. This is going to be a unreactive intermediate, and it's going to just stay there until we had H2O. And this basic amine with a minus charge is going to grab a proton, giving us our imine, or our carbon nitrogen double bond. And if you add acid and water, it's going to go to the carbonyl. And so now I'm going to show you the mechanism of how acid and water takes us to the carbonyl. And realize the mechanism is going to be identical for either this case or this case. It doesn't matter your substituents on the carbonyl carbon. The chemistry is going to be the same. So I'm just going to show the mechanism once, but it's going to be the same for the case I show you, as well as this case. So if you throw in acid and water, we get the ketone. So nitriles, you can make ketones with using Grignards or organolithiums. And if you use dipol, you can make aldehydes. So nitriles are a great way to make carbonyls. That's right, green is lame, right? And I should mention right now, every step in this, every single step in this is reversible. And I also want to mention, this is acetal chemistry. So me showing you this mechanism, I'm also introducing or segueing into the acetal portion of this class. So if you take this molecule and you throw in H3O, which part of this molecule do you think is going to be protonated? Which of this molecule do you think is going to be protonated? That's absolutely. The lone pair of electrons and nitrogen are going to be somewhat basic. It's an sp2 nitrogen and an sp3 nitrogen, so they're not as basic as a typical amine, but they're still a lone pair of electrons and a not very electronegative atom, so they're going to be somewhat basic. So it's going to grab one of the protons, giving us what we call an iminium. So the chemistry name for this is not a carbon-nitrogen double bond. This is an iminium. And then when you have a positive charge in an imine, we call them iminiums. M-N-E-M. Try saying that 10 times fast. So imines with a positive charge are iminiums. So we form this. And of course this is acid base, so it's reversible. The next step is the water is going to add the carbonyl carbon of the iminium. All right, and that's going to give us H2O plus and our neutral amine. So do you think this is going to stay like this very long, or is there going to be a basic thing that's going to go and grab the proton from the water intramolecularly? Yeah, there's an amine. There's a an amine right here. So this is amine. This amine, lone pair of electrons, is going to grab the proton from this thing. And so this is what we call a proton transfer. And we're going to be talking about a lot of proton transfers. And there are two types of proton transfers. There are intramolecular proton transfers, where the proton transfers occur between the same molecule. So this is intramolecular, where one part of the molecule takes the proton from another part. And then there's intermolecular. An intermolecular would be an example of this, where this takes a proton from a second molecule, the H3O. So this would be an intermolecular, taking the proton from a different molecule. This would be an intramolecular, taking the proton from the same molecule. As far as what people draw, in a lot of cases, you'll find you can draw both, and both are logical. So as long as both are logical, then by all means, it doesn't really matter if it's intra or intra. But there are some cases where it becomes obvious there's going to be one's going to be favored. And in this case, it's in a case such as this, I think the only option is really intramolecular because you have this really acidic proton right next to this basic amine. Yes?
Is the R on the right still the butyl?
Yes. Okay, good catch. So this amine is going to grab this proton. And as far as intermolecular, if there's no acidic proton in your molecule, then it kind of has to be intermolecular. So in this case, this taking a proton from H3O, that's intermolecular because there's no other option. But a lot of times you will see there's going to be both choices. And most cases it doesn't really matter in my opinion, as long as it's reasonable. If it's unreasonable, i.e. if you're committing a pKa crime, so you're taking a proton that's not really acidic, then that's wrong. But as long as it's a reasonably acidic proton and the pKa's work out, it doesn't matter really in my opinion if it's intra or intramolecular. Professor Bergdahl and I have this long-coming debate, because if you haven't noticed, I'm very much an intramolecular guy. And Professor Bergdahl is an intermolecular. He told his class last time he taught this, no intramolecular proton transfers ever. And I'm like, no, it makes more sense to do some intramolecular sometimes. So it's a tomato-tomato thing. Again, there's way too many ways to skin a cat. That's an old saying, right? I swear that's not my saying. My wife's a veterinarian, they would never skin a cat. So now that gives us this intermediate. And I'm going to move this over here. Whoa, I just destroyed a marker. That was my Vanderveer moment. Those who left probably had Vanderveer or Biochem. So, you have this intermediate, where now it's NH3 plus, and now, in this case, since it's cationic, it's going to be a fairly good leaving group. So now we can kick off the ammonium, and this will give us our protonated carbonyl, plus ammonia, and then the ammonia is just going to grab the proton to give us our ketone plus NH4 plus. So just going through this mechanism real quickly. First up is protonation of the nitrogen, making it a very, very strong Lewis acid, because now, since this nitrogen has a positive charge, that means this carbonyl carbon is going to have an even bigger positive charge since it's less electronegative. Yes?
Since the conditions are fairly acidic for the reaction, is it possible to form the alkoxy before the amine leaves?
No, because it's acidic. If you do this under basic conditions, absolutely. And you can do these under basic conditions. They don't work nearly as well. But if you did this in basic conditions, you would form the alkoxy first. But in this case, you wouldn't. Yeah, because it's acidic, yes.
On the test, do we need to draw the electrons pushing from the hydrogens that are getting stolen?
Sounds good to me.
Yeah.
That's a key mechanism of the proton transfer, so yeah.
But no, I'm saying so you've got one arrow drawn from the lone pair of the nitrogen to steal the hydrogen, but you don't have anything coming from the...
Oh, you mean, so the H3O going to H2O?
Yeah.
That's not bad. I don't draw it, that shows you what I think, but, better safe than sorry, I'd say. Or you could just, instead of drawing H3O, you could just draw H+. And there's not a problem. So we pronate the amine, then water is going to add. to give us this intermediate, which is quickly going to favor this one because this is an acidic hydrogen next to a basic lone pair. So the basic lone pair takes the proton to give us an ammonium, and then the lone pair of electrons in the OH are going to kick down, kicking up ammonia, giving us protonated carbonyl plus amine. The amine is going to grab the hydrogen to give us our ketone. So this is how a amine or aminium are hydrolyzed to carbonyl. It's a good mechanism. It's also the beginning of acetal chemistry. Because this mechanism you just went through is pretty much an idyllic, and a classic, if you will, acetal. And so let me actually introduce what acetals are and some of the chemistry in the last few minutes. I'm going to go OHOH in this case. So acetals are derivatives of carbonyls, and so this is well, technically, I'm calling it acetal, but technically it's a ketal because it's from a ketone. So under acidic conditions, ketones and aldehydes are in equilibrium with a hydrate. So do you remember we were talking about the Jones oxidation? And we form the aldehyde first, and then I said under acidic and water conditions, we form a hydrate, and the hydrate's oxidized to give us the carboxylic acid. This is that chemistry. So under acidic conditions, carbonyls are in equilibrium with their acetal. And in this case, I have HO across it, so OHOH. You're not limited to water. Alcohols will do the same thing. Just to show you an example, if you take methanol and H3O, you'll come to equilibrium with O-methyl across the carbonyl. And so let me show you the chemistry how this forms. And then we can maybe talk about the Jones reagent and how that forms and leads to the oxidation. And that will lead us probably in a good place to start for Friday. And I want to mention this mechanism is going to be very similar to the mechanism we just talked about with the amine hydrolysis. So if you have a carbonyl and you're under acidic conditions, what do you think is going to happen? Reversible. Protonating the oxygen, absolutely. So I'm going to go H+, so I don't have to draw the other arrow. I'm learning. So we're going to get this. I'm just going to leave this on. So when we pronate the oxygen, what we do is we make this carbonyl a real killer electropile. Because normally there's a partial positive charge on the carbonyl carbon. But now since the oxygen's positively charged, what that means is all that new positive charge on the oxygen is really going to be focused on the carbonyl. So one way you can think of this is almost like an alcohol that changes into a carbocation. Whenever it equals, this is a resonance. So once we protonate the carbonyl, we're putting some mega partial positive charge at the carbonyl carbon, as you can draw using this resonance structure. And so what that means is now fairly weak nucleophiles, like methanol. So So typically, the only thing we've really added in the carbonyl so far are really strong nucleophiles like H- or Grignards or organolithiums. Now in this case, you can add weak nucleophiles like methanol or water. I'm just going to do water now just because I already did it. So now water can add into this, and again reversely it's going to give us H2O plus, neutral OH. It can give us this intermediate here, but we're under aqueous conditions. So now you can imagine one of these waters can do an intermolecular proton transfer. To give our hydrate. So hydrates are simple things to form. So when we use water and acid, and we protonate this and the water adds, we just need one proton transfer. Can everyone see this? We just, what? Do you want to try and move this down a bit? So now we have our, what we call an acetal or a ketal. Or we previously would call it a hydrate. So under aqueous conditions, this mechanism over here explains these two equilibriums I drew up here, which under acidic conditions are in equilibrium with either a hydrate or I guess I'll call us our alcoholate. Here. So in other words, under acidic conditions, we can make weak nucleophiles add in the carbonyls to give us these metastable intermediates. Where you, instead of having the carbon-oxygen double bond, we have two carbon-oxygen single bonds. And so now, when we talk about Jones, right, and with the Jones chemistry we talked about, it's just review. We take a primary alcohol, so fluoric acid, the chromic acid. We do a Jones oxidation that initially gives us the aldehyde. But since we're under acidic conditions from the sulfuric acid, we will reversibly protonate the carbonyl, giving us water from the H3O. Have this add in.